Okay, so for part 2 of homework 7-5, we're picking up with question 5. And this question is actually a little bit misleading. They give you a whole bunch of information here. So they give you the disc mounted on frictionless bearings here, and it's rotating at a 30 RPM rate. Then a thin-walled hollow cylinder is then dropped onto that disc. It's released from rest just above the turntable. The hollow cylinder slips on the turntable for 20 seconds until they acquire the same final velocity. What is the final angular momentum of the system? So again, they give us a ton of information here, right? The key concept, though, is the fact that in this collision, because the cylinders just drop down on top of it, right? So you've got your hollow cylinder here. So I'll do the best I can to draw this. I know my cylinders are rarely very good, but that's okay. So there's my hollow cylinder. It's very thin wall, and then I've got my disc that's beneath that that's rotating, right? So I've got my disc. Pretend that's a better disc, but that disc is rotating. So the cylinder drops down on top of it. They kind of slip on top of each other until eventually they reach the same speed. The concept here, though, is there's no outside torque. By dropping this down perpendicular on top of it, I'm not producing any type of force or torque on the disc itself. In fact, the only torque would be the friction between each of these two objects, which would always be equal and opposite between them. So if we're regarding this whole thing as a system, again, there's no outside torque on the system. And the big conclusion there is if the net torque, if the total sum of torques is 0, then angular momentum is conserved. So this becomes much like question 4 and much like question 1, it just becomes a conservation of momentum problem. Now the reason I said this question is not as bad as it looks like, what are they asking us to find? Well, they're just asking us to find the final angular momentum, right? Which maybe at first we're thinking, okay, we need the final moment of inertia times the final angular velocity. But don't make it that complicated. If I need the final angular momentum, don't I just need to know what the initial angular momentum is? Since it's conserved, those two numbers should be the same value, right? So that's where this problem gets hopefully very easy. All I really have to do is find my initial angular momentum, right? So to do that, I just need my initial moment of inertia. So in other words, the moment of inertia for just the disk, and then I need the initial angular velocity, which they gave me RPMs. I just need to convert that to radians per second. So I'm going to go ahead and do that first. So my initial angular velocity is 30 revolutions per minute. I want that in radians per second. So hopefully a conversion everybody at this point is pretty comfortable with, but if you need to see it, obviously here we go. So just calculating this, and it actually works out very nicely. So 60 pi over 60, which obviously then means the initial angular velocity would be pi, or obviously if you want to round that off, 3.14, 15, etc., etc., etc. So you've got your angular velocity to work with there too. So then I just have to find my initial moment of inertia, and again, we're simplifying this because by finding the initial one, since the cylinder is not moving, I just need to find the rotational inertia, the moment of inertia for the disk itself. So they tell me it's a uniform disk. I know the moment of inertia for a uniform disk is 1/2 mr squared. They give me the mass, they give me the radius, and I've got my angular velocity. So at this point, it's just a matter of plugging everything in and having a wonderful time. So doing that, right, 1/2, 3.7, the radius again 0.4, which I need to square, and then times pi. So as I do that, as I calculate this number, I end up getting about 0.296 pi, or again, if you've rounded that off, about 0.930. And my units for angular momentum, what would they be? Well, what are my units for moment of inertia? It's kilograms times meters squared. And what are my units for the angular velocity? It's just radians per second. Keep in mind, though, radians aren't really a unit. They're just kind of representing a measurement. So my final unit would be kilograms times meters squared per second. So again, there's my final answer. Hopefully this one wasn't too bad as soon as we realized conservation of angular. Okay, so question 6, a very classic representative of a force problem here. We've got an 82 kilogram diver standing over here, which means we do know his force of gravity as it's pulling down. The length of the board is given. It does tell us also that it is a light board, indicating we're not worried about the mass of the board, so we don't have to have an additional force of gravity from the middle, which simplifies this one a little bit, obviously. But it's supported by these two narrow posts. We want to figure out what is the force exerted by each of those pillars on the diving board, right? So we're trying to figure out what the force of A and the force of B are on this diving board. Well, the first thing that I would encourage you to do is think about the forces here, right? We know the force of gravity is pulling down, and since the system's not moving down, that means at least one of these is going to have to be pushing upward, right? But the question is, are they both pushing upward? Is B pushing upward and A pulling downward? Is A pushing upward and B pulling downward? Right? We really have three different possibilities of different combinations. So we have to think about how we can confirm which way this should be going. And the easiest way to do that is to choose a pivot point, right? Start thinking in terms of torque instead of just force. And so let's choose over here. Let's choose this contact point to be our pivot point. We know that the board is not rotating about that pivot point, and therefore the sum of torque needs to be 0. So since the sum of torque needs to be 0, the torque produced by beam or pillar B and the torque produced by the force of gravity have to be equal and opposite, right? They have to add up to be 0. So since the force of gravity would be causing about this rotational point here, the force of gravity would be causing the board to try to rotate downward, the pillar is going to have to be causing it to want to rotate upward, which tells me then that the force exerted by pillar B has to be going upward. Right, so I now know that for sure. I know that pillar B has to be going upward. And at this point, to be honest, if we wanted to, we could definitely just set that up and calculate. So we could say the torque caused by the force of gravity needs to be equal and opposite, again, to the torque caused by pillar B. And as soon as I realize that, if I'm choosing this to be my pivot point, well, this is just force of gravity times the radius equals, again, I'll call it maybe TB here just to be the tension or the force of B. Actually, let's just call that FB, the force of pillar B. And then the radius to pillar B, so I'll call that RB to distinguish that as well. So the force of gravity would be 82 times 9.8 times the full radius from the pivot point, and that is 5 meters in this instance. And then the force of B, which I don't know, but I do know its radius would be 1.6 right, meters from the pivot point. So obviously if I look at this equation, that actually gives me a very easy route to find the force of that pillar B. Right? And so when I solve for TB or FB, I get 2,511.25 newtons. Obviously you can round that off a little bit more than I did, but I've rounded it off to a couple significant digits there. But anyway, I can calculate that number without too much trouble. So I've actually answered part B already. So getting that out of the way. So then the question is, how do I find the force exerted by pillar A? And the answer is we could either do the exact same thing I just did, except choose point B to be the pivot point. So now I could choose this as my pivot point. And that actually helps me determine the direction of pillar A. Right? If I choose this to be the pivot point, the force of gravity from the person would still be causing this clockwise rotation, which means pillar A needs to be causing a counterclockwise rotation, which means it needs to be going this way. And so that tells me then that pillar A actually has to be holding the beam downward. So the force exerted by pillar A actually has to be pulling downward on the beam. Otherwise, if pillar A is pushing up and this force of gravity is pushing down, this system would be rotating around in the clockwise direction, which obviously is not happening. So that's how I know that. The other thing I could do at this point that would be pretty easy is just take a step back and go to forces. I know that the sum of all of the forces, right, the total sum of forces has to equal 0. So in other words, FG plus FB plus FA has to equal 0. Well, since I know FG is pulling down, I'm going to make that negative, so negative 82 times 9.8 plus pillar B, which is pushing upward, so I'm going to define that as a positive 25,1100.25. And then I don't know what the force of pillar A is doing, although I now know it should be negative. Let's pretend we don't know what it's doing. Right, so if I set this up, when I end up solving this equation, it confirms that A ends up being a negative number. So you end up getting the force of A is negative 1707.65. And again, the significance there of it being a negative number, and I'm going to go ahead and drop the negative, but the significance of it being a negative number is that that is pulling downward. Right, so this is pulling downward, whereas the force on B is pushing upward. So make sure you're pretty comfortable with these types of problems. As always, as with most of our torque problems, the pivot point, the choice of pivot point is crucial. Right? By choosing a pivot point, I want to eliminate one of the two unknowns. But anyway, hopefully this one wasn't too bad to get through. Okay, so question 7, probably the last question I'll get to in this second part of the video here. But anyway, it's a good question. It's a ladder problem, which I know can be kind of tricky. And then this one gives us a little bit of twist by having us work it kind of backwards from what we're used to. So anyway, we've got a 5 meter long, 12 kilogram ladder. So the length of the hypotenuse here is 5 meters long. The 12 kilograms of force of gravity caused by that would be pulling straight down right from the center, so 2.5 meters up from the ladder there. The coefficient of static friction is given to us, and then they give us the length here from the base. So they give us this to be 3 meters. We know the hypotenuse here is 5 meters, which tells me the height of the wall would be 4 if that ends up coming into play. Maybe it will, maybe it won't, but we'll see. But anyway, the coefficient they give us, which is where it's kind of backwards. A lot of questions, they'll usually ask you to find the coefficient of friction, but they give us that measurement. Instead, they ask us what distance measured along the ladder from the bottom can a 60 kilogram person climb before the ladder starts to slip. So they're asking us basically for what distance up the ladder here, so measured along the ladder from the bottom. So what distance up the ladder can a 60 kilogram person climb before the ladder starts to slip? Well, if this is the coefficient of static friction, we can use that to help us find the maximum force that static friction can supply. Right? So we're going to try and find the maximum force that static friction can supply, which would be equal and opposite, we know, to our wall force. And the significance of that is that would then, if I can find that number, that would allow me to then use torque and to work backwards to figure out how high up the ladder he can walk, or this person can walk. But anyway, so let's try to find our frictional force. Well, we know friction would be the coefficient times the normal force, and obviously they give me the coefficient, 0.28. So I just need to think about what would be the normal force exerted at the bottom of the ladder. Well, you obviously have the force of gravity of the ladder itself, plus, regardless of where this person is, the person's force of gravity is going to be pulling straight down as well, right? So if I think in just in terms of forces, the normal force plus those two force of gravities need to be equal to 0, right? The total sum of forces need to be equal to 0. So since both of these are pulling downward, I'd make that negative. So in other words, the normal force needs to be equal and opposite to the force of gravity of both the ladder and the person. So all I have to do to find my normal force is find out what the force of gravity of the person and the ladder is. So the 12 kilogram ladder times 9.8 plus the 60 kilogram person times 9.8, multiplying those two numbers again to find my normal force. And when I do that, I find my normal force to be about 705.6, so about 706 newtons of normal force. Again, no torque came into play for this yet, right? This is just using forces to help me find that. But anyway, now that I know my normal force, I can plug that in to find my frictional force, right? So friction would then be the coefficient, the 0.28, times 705.6 or 706, depending on if you rounded that. Okay, so the maximum frictional force, that's what this is telling me, right? This would be the maximum frictional force. The maximum that friction can be ends up being about 197.6 newtons of force. Okay, so again, that's representing the maximum friction. So anything above that is when the ladder would start to slip. So this becomes our critical point, if you will, right? This is the value that we want to figure out. How high can you get up the ladder before friction has to supply this much force, because that's going to be the kind of the slipping point, if you will. So I've got that number to work with. And so this is where it becomes very similar to what we would normally do for a ladder problem, right? So I'm going to take for granted that most of us know for a ladder problem we're taking advantage of the net torque being 0. Again, to simplify it, by eliminating both the normal and the frictional force, I'm going to choose my pivot point to be the bottom. So what that tells me then is the torque caused by the person plus the torque caused by the ladder needs to be equal and opposite to the torque caused by the force of the wall. Well, the force of the wall is just the same in magnitude as the frictional force, right? So the torque caused by the person would be the force of gravity of the person times the radius of the person times the sine of the angle that that force makes with the ladder itself. And that is something you have to watch out for. Plus the force of gravity of the ladder itself times the radius of the ladder, again times the sine of the angle that the ladder makes with the ladder, or the force of gravity of the ladder makes with the ladder. And then finally, the force of the wall times the radius of the wall, and then times the angle that it makes, the sine of the angle that it makes with respect to the ladder. And so at this point, I hope we are pretty comfortable plugging in. Again, the force of gravity of the person is the one I'll do first. So 60 times 9.8 times the radius, which I don't know, and then times sine of the angle. Well, if the angle is 53.1 degrees with respect to the ground, then it would be the complement of that. It'd be 36.9 would be the angle that it makes with respect to the ladder. So I'm going to use that for both the force of gravity of the person and the ladder. So as I plug in here for both of those, I'm using the 36.9. Whereas for the wall, which again I know the wall force is 197.6, the radius of the wall would be the full 5 meters, and then the sine of the wall here would be the sine of 53.1. I'm using the original angle. I did make a mistake over here. I should have included the distance for the ladder, so 2.5 with this measurement as well. Anyway, I know I'm running short on time. I hope you're okay with the setup of this process. I do want to go ahead and write the answer. So your answer that you should get would be about 1.74 meters up from the base of the ladder. So that's how high he can climb if I calculate this measurement. Anyway,